Alright, so let's continue graphing some more quadratic equations. In this video, we're going to look at equations with irregular roots, and you'll see what I mean by that in just a second. It's not going to be like the graphs we've been seeing. So if we're going to convert into root form, we would normally try to factor this. So we would set up this x here. Factors of 5 are 1 and 5, factors of 6. They're both going to have to be negative, so we can add to a negative number. We could have -1, -6. That's not going to work. We could have -2, -3. Switch those around. Eventually, if you haven't already seen, eventually you will see that this problem is actually not factorable. This equation is not factorable, so we can't convert to root form. So the next thing to try is going to be vertex form. And to get vertex form, we know that we can complete the square, start that process. So we'll factor out a 5 from there. Then we'll change this to x minus 1 squared, x squared minus 2x plus 1. So we take out the 1. Bring this minus 5 to the outside, plus 6 will be plus 1. So we see that the vertex is 1, 1. Now we want to find the roots, and we can easily do that by continuing with completing the square process. So we know the roots on this x-axis, that's where y is equal to 0. So now we're going to set 5 times x minus 1 squared plus 1 equal to 0. We replace the y with 0 since y equals 0 for the roots. So now if we'll move this 1 to the other side, we will get 5 times x minus 1 squared equals -1. Divide both sides by 5. Now we take the square root of both sides, and we are going to be left with the square root of a negative number. Square root of -1/5 is I times the square root of 1/5. So we have an imaginary number here. The roots are actually going to be, don't forget the plus minus there. The roots we have I times the square root of 1/5 plus 1. So the roots here are imaginary. So imaginary roots, we don't see them on the graph. So we actually don't have any real roots, any roots that we can plot on the x-axis, which means the graph never crosses the x-axis. So how is it possible? How is it possible that we have no roots here? Well, it's because the parabola is opening upward here like this, and since the vertex, we're already starting at a positive y value, we just never go all the way down to the x-axis. Another way to prove this is to use the discriminant. Remember, the discriminant is the part of the quadratic formula under the square root, b squared minus 4ac. So if we take the discriminant of this quadratic, b squared, that will be -10 squared is 100 minus 4 times 5 times 6. 4 times 5 times 6 is 120. So 100 minus 120 is -20. And when we have a negative discriminant, we have two imaginary roots, which we proved down here, that the roots are imaginary. We don't actually see them on the graph. So the graph never crosses the x-axis. So now if there's no roots and all we have is a vertex, then how can we graph this? Well, we can use the y-intercept, the point where the graph crosses the y-axis. On the y-axis, x is equal to 0, so we can substitute 0 for x in the equation. So if x equals 0, y will equal 5 times 0 squared, that's 0, minus 10 times 0, that's 0, plus 6. So y is just going to be equal to 6, and we get the point if x equals 0, y equals 6. That's the y-intercept, the point where the graph crosses the y-axis. Now, because we know that this parabola has an axis of symmetry going right through the vertex, we can reflect this point over that axis and get this point right there. And now we have 3 points, which is enough to get us a decent looking graph, just like that. So even though the graph has no roots, we couldn't use root form, we're still able to graph it. So that is one type of irregular quadratic, because most quadratics, at least that we've done so far, have had 2 roots. They've crossed the x-axis twice, which meant we could use root form and factor them to find roots. So now we're going to do another type of irregular problem here. We're actually going to start in the root form, so we know we're going to have roots. So with the root form, it's very easy to see what the roots are. We just say, what do we need to make x equal to in order to get y equal to 0? Well, in this one, we'll need x equal to 3. And in this one, we will need x equal to 3. And here's what's irregular about this problem. How could we get the same root for both of these factored terms? Well, that's because it is a duplicate root. Both of these factored terms produce the root of 3 right there. So we do have technically 2 roots, but since they're the same number, they're right on top of each other, and they're both 3. So when we look at the graph, it's only going to cross this x-axis at x equals 3. In fact, really, it's not even crossing it, it's just touching it. So even though we do have technically 2 roots here, the duplicate root that's the same number, on the graph it's just going to look like one root, one point where we touch it here. Now we can prove the reason there's one root in this problem, again going back to the discriminant. Here we saw that since the discriminant was a negative number, we have no roots. But remember that if the discriminant equals 0, we have exactly one real root. So let's see if that holds true for this problem. B squared minus 4ac. Well, the first thing we're going to have to do is put this into standard form so we can see what a, b, and c are. So we're just going to multiply this out. We'll get y equals 2x squared minus 6x minus 6x is minus 12x. Negative 6 times negative 3 is plus 18. So now we can find the discriminant. Let's give ourselves a little more room. Okay. The discriminant is going to be negative 12 squared is 144 minus 4 times 2 times 18. That's going to be minus 144. And we get 0, just like we predicted. Discriminant of 0 means that there is only one root. And again, if you're not quite sure why that works, you can go back and watch the video on the discriminant and see exactly why that holds true. So now, in this one, with this one, since we also only have one root, we don't have a second point where it's going to cross the axis to make it easier to graph, we could again go to the y-intercept to help us graph. So the y-intercept being what is y equal to when x equals 0 on this y-axis. And we can easily substitute x equals 0 into this equation. If x equals 0, y is going to equal 18. Now here's the problem with that. 18 is way off the graph up here. So the y-intercept isn't going to help us. It's going to give us a general idea that the graph is very steep going up this way. But we want another point that we can actually plot on this grid that only goes up to 10. So here's what we can do. Let's go back to the root form here. And let's factor out a 2 from this 2x minus 6 term. let's do it down here. So what we're going to do is, we know that we got x equals 3. To get either of these equal to 0, we got x equals 3. We proved that here. Now, when we factor out a 2, you're going to see why that happened. If we factor out a 2 from this, we'll get 2 times x minus 3 times x minus 3. So really, these were the exact same. It's just that this had been multiplied by 2. But multiplying it by 2, x is still the same number in order to get it equal to 0, because when we factor it out, we get the exact same thing. Now, if we continue simplifying this, we will get 2 times x minus 3 squared, because this term is just multiplying by itself. And now here's where you can draw a big connection, because now we're left with an expression that is technically in vertex form. Because look at this, we have x minus 3 have a times x minus b squared plus c is obviously 0 since there's nothing there. So if we approach it from the viewpoint of it being in vertex form, then we see that it's y equals x squared. It's been shifted over to the right by 3, meaning x is equal to 3 in order to get y equal to 0. We see that here. That's just the root. And now we have a 2 out front. So remember that if we're graphing in vertex form, the easiest way to do that is to remember the pattern as x changes by 1, y changes by plus 1, then plus 3, then plus 5. That pattern times whatever the coefficient is out here. So since it's 2, we're going to be going up 2, up 6, up 10. So let's do that. We're going to go up 2, then we're going to go up 6, and now we can just reflect those points over the axis of symmetry, dividing the graph. And there we go. Again, you see that we never quite reached the y-axis because the y-intercept is 18 all the way up there. Okay, here's another problem where we're starting in standard form. So if you want to try root form first, try to see if we can get some roots out of this one. We would factor it. So the first thing we would do is factor out a negative. You don't want to have a negative coefficient of x squared, so we're going to factor out a negative from the whole thing. And now we would try to factor this. So the only factors of 5 are 1 and 5. For negative 3, we could have 1 and negative 3. This would be 2, so that wouldn't work. This would be negative 2. That's not going to work. I don't remember what we've already tried, but we're not going to get to 10. No matter what we do, we're not going to get to 10. This is another one that is unfactorable. So you might assume, well, it's unfactorable. That must be because, like in this one, that was also unfactorable. There were no roots. But that is actually not true, and you'll see why in just a minute. This one does have roots, even though it's not factorable. But before we get to that, let's start with what we can do. If we can't get the roots, we can get the vertex by completing the square. So we are going to go ahead and do that. In fact, I think it's going to be a bit easier if we actually just erase that and start completing the square from the original form, since we don't already have that negative factored out that we have to deal with. Because now we can factor out a negative 2 right out of here from the first two terms. Sorry, not negative 2, negative 5, okay. And we go through this process, which hopefully should be very familiar by now. And there is the vertex. So now here is where we know that there actually are two roots for this graph. Because look where the vertex is. The vertex is above the x-axis. And the leading coefficient, either in the vertex form here, the -5, or in the standard form, it's also -5, the coefficient of x squared. It's negative, and we know that if the leading coefficient is negative, the graph, instead of opening upward, it's going to open downward. So if it's opening downward and starting at this vertex, then eventually it has to cross the x-axis on both ends. So because of that, we know that there are two roots. So now why wasn't it factorable if there are two roots? Well, it's because we can't get the roots by factoring. Remember that sometimes factoring doesn't work even if there are real roots. In that case, we're going to have to find them by either using the quadratic formula or completing the square. Completing the square is going to be easier since we already started the process here. So let's just continue that. So we're going to set, to find the roots, we set y equal to 0. So we change that to 0. And then we can just copy down what we already have here. And now we're going to finish completing the square with y set equal to 0. I'm going to divide both sides by -5. Take the square root of both sides. Okay, now to get the final solution for x, now we could do a lot of stuff with what's inside here. We could change square root of 8 to 2 times square root of 2. We could rationalize this denominator. But we're actually not going to do all of that extra simplification because all we want to have is something we can graph. And square root of 8 over 5, we're going to want to end up approximating this. So this is pretty simple to figure out about what this is going to be equal to. If we start simplifying it and adding in more square root signs and all that, that's just going to make it more complicated. So while this technically isn't a fully simplified answer, we're going to leave it at this. So our two roots are square root of 8 over 5 minus 1 and negative square root of 8 over 5 minus 1. We obviously couldn't get those by factoring because we have a square root here, which you can't get by factoring. So it is a real root, just to make sure the terminology is clear. This is a real root because there's no imaginary numbers, but it is not a rational root. It has a square root, which makes it irrational. Okay, so now that we have our two roots, we want to plot them on the graph. So we're going to have to estimate about where they are, since they're not rational numbers. So square root of 8 over 5. 8 over 5 is 1.6. Square root of that's going to be around just over 1, 1.2, 1.3. So we can actually keep it pretty simple. It's close enough to 1. Let's just round it off. So this is going to be approximately equal to, that's what that little notation means, two squigglies. This is about equal to 1 minus 1, which is 0, or negative 1 minus 1, which is negative 2. It's close enough that we can plot it there. And we see that it's going to work out pretty well because these 2 points are an equal distance away from the axis of symmetry, so they can be reflected over each other. It's kind of a lopsided looking parabola. Let's see if I can do that better. There we go. Okay. All right, and we are going to stop there. I think we've covered enough irregularity in this video. But this was just to show you that not all parabolas follow the standard rules, so when they don't, you have to think outside the box a little bit. You can try the y-intercept. You can try proving how many roots there are going to be with the discriminant before you start graphing, just so you know for sure. You can, in a problem like this, convert from the root form to the vertex form, and then use that method of graphing. Or if you ever get really stuck, you can always just start plugging in values for x and seeing where they end up for y values. Although, if you are comfortable with all these methods, you shouldn't run into that problem. But that is always going to work. And there are no exceptions to that rule. Any function, you can plug in any value for x and get the correct value for y. So again, hopefully you see that we really are pulling together everything we've learned about quadratics, whether it's factoring, discriminant, simplifying, completing the square. It all pulls together. It's all very important. So I believe in the next video we're going to shift gears a little bit and go to quadratic inequalities. That'll be interesting. We haven't looked at inequalities in a while, so let's see what they look like.